simplest one, right? So the simplest one I can imagine is sort of like, let's say you have a tank, right? You have a tank, and you have flow going in. You have flow going in, and you have a particular level there. And what happens is that you have flow coming out the bottom of this tank, right? You have flow coming out the bottom of this tank. So what happens is that the flow rate going in is, let's say, Q in. Let's say flow rate going in is Q in. And what happens is that the flow rate going out there, so you learn this from fluid mechanics, right? Or, I'm not sure I even want to bring down the idea of the Bernoulli's equation, right? Let's just do this the dumbest way possible, right? So the dumbest way I think about this as a high school student goes something like this. If we ignore the viscosity, right? If we ignore the viscosity of the water, and we just say it's viscousness, then how do we get the velocity of the flow coming up? Well, if the water has no viscosity, packets of water don't see any other packets of water. You see what I mean? There's no viscosity. And so as far as like a packet of water that's like up here, right? Packet of water that is up there, what happens to it? It's equivalent to have a rock that you drop from that height. Do you see? Because it doesn't see the water. If you say something has no viscosity, it's as if the water here, a packet of water here, doesn't see anybody else. Does that make sense? Right? So it's like a rock that if you drop from there, well, it goes down. You see? So what would be the terminal velocity of a rock that you drop from some height? It will be the kinetic energy, or the potential energy gets converted to kinetic energy. Right? And so when you go through that, what do you find out? That the velocity is equal to? So you have something like, what's the potential energy at that point relative to this height? So the potential energy is rho gh, right? That would be the potential, not the rho gh, it would be just gh, right? That would be the potential energy per mass, right? So you have an object there of some mass. So gh is the potential energy per mass. Did you see? So what is the kinetic energy per mass? It will be 1/2 mv squared. But if we say per mass, we have divided across the m already for 1 kilogram, let's say. So you have 1/2 v squared. So the terminal velocity of a rock that you drop from that height, or a packet of water that does not see all the other rest of the water because the viscosity is 0, right? Then what you end up with, the velocity is going to be equal to square root of 2gh. Does that sound familiar? It's one of the F stuff you memorized when you were in high school physics or something, right? Formula sheet. I hate formulas. Okay? And then, of course, you can do this by the so-called Bernoulli's equation. Right? You know, I find out that if I'm loud enough, everybody closes their doors. Yeah, she's laughing at me because I'm loud. Just joking. Well, at least it's cooler, right? Because I am so hot here. I'm doing jumping jacks in front of you. Okay? All right. So, square root of 2gh. Of course, you guys also saw this before from the perspective of Bernoulli's equation in fluid mechanics, right? So you learn this in two different ways. In fluid mechanics, one way to do this, you say, oh, the pressure down here at this point, the pressure is rho gh. You remember that? Right? That's the pressure there. The pressure on the other side is what? Is atmospheric, right? So you set that to pressure of 0, let's say, right? And so what happens is you have what you have? You have a delta P, right? So remember in Bernoulli's equation, delta P divided by rho. So the pressure here is rho gh minus 0 divided by rho. So you have gh. Then you have the changing kinetic energy. The kinetic energy here, you said far away from the hole is velocity 0. The velocity on the other side is, well, that would be the velocity of the stream coming out. So in fluid mechanics, you also learn that as V is equal to square root of 2gh. And again, in fluid mechanics, you also learn this the other way. The velocity up here, right, is what? Is, let's say, 0, because let's say this hole, the flow rate is fairly small. The hole is small relative to the area of the top, so the velocity at which this interface is declining is negligibly small. So you said the velocity there is 0. The potential energy per unit mass is gh. Did you see? And down here, you say the velocity at this point, right, plus the without the potential energy, you came up with exactly the same equation. And fluid mechanics, did your professor give you a name for this? It starts with T. Torricelli's equation or something like that. I forget the name, but that's the 3 different ways that you guys have learned this in fluid mech. Is that clear? So simple. And so what happens is this is the velocity of the water or the fluid as it shoots out. Did you see? So what is the flow rate coming out of this tank? It'll be equal to the velocity, the average velocity coming out multiplied by the size of the hole, area of the hole. You see, I just call that AH. Does that make sense? So the volumetric flow rate going out, Q out, you're going to say is what? The size of the hole, AH, let's say, multiplied by square root of 2GH. Does that make sense? So you might ask, well, why do you call this thing AH? Because I want to reserve this cross-sectional area of the tank for the letter A. Okay? All right. So one of the things later on, just as a comment here, because I noticed there are some people who are not here. It goes something like this. Eventually when we have the quizzes, right? The way I will have you guys do the quizzes is you do them by hand on a piece of paper, everything closed, right? Nothing open. And then at the end of the quiz, you take a picture of it, right? And then I will have a particular assignment or something like that, and you're gonna upload that picture of the work that you did, of that thing that is solved. So that thing is closed, everything closed, right? Take a picture of it, okay? And upload that. So, as you can see already, right? That like, how many ways can you get an A in this class with a total score, possible score of 220, right? So hey, if you want to get 0 on like the quizzes, yeah, you can still get an A. Just simply do, a few stand-up presentations or do some more of the AI projects or something like that. There's no way you don't get an A in this course unless you absolutely don't want to. Do you see? Does that make sense? Right? But the purpose of the quizzes is so, you give it a try. Do your best. Okay? But if we go down the line of like not showing up in class, something like that, well, that's going to be a bit problematic because once you go down that line, you zero out the quizzes. Yeah. And if you are a perpetual absentee, trust me, I would target you and set up the quiz when you're not around. What's that? Yeah, I think what happened is the way I did it for heat and mass transfer just did not work. I felt that was just, that was crazy. I've never seen attendance of that level ever in my 26 years at UC. What happened there in heat and mass transfer. That was just unbelievable. All right, so we got this. V is equal to square root of 2GH. So Q out is there, right? And so now the next thing is, what do we want to do? We want to simulate, right, how the height of this tank varies with time. And why might it vary with time? Because the flow rate coming in might change with time, let's say. So how do you go about doing this? Do I have a volunteer here? So, let me repeat this a gazillion times. You guys have heard me this a million times. Okay? When you see me teach and do this in front of you, right? Remember, it's not enough for you to say, I understand. Or you can say, oh, I can solve this problem. I regret to inform you that your ability to understand this and understand and do it is pretty much almost at this point, almost worthless because of the AI, right? This is like a ridiculously trivial thing. So what you would end up having to do is you need to be able to talk it out. The entire engineering is besides understanding the answer key, which is the AI result, understanding the answer key. You know the answer, you see the answer key, right? There's no problem as an undergraduate engineer that you would, pretty soon shove it into AI and get the result out because there's no chance you could do it better than AI. No chance, right? And so you're looking at the answer key. You need to be able to express that out. So when I'm teaching you this class, the emphasis I can't repeat enough to you. Do not focus on what I'm writing there. Focus on the way I am saying it. Right? That's what you're learning from me, is to how to convey that idea. That's the most important thing you want to get out from this class. There's no way you're not going to get an A if you don't, unless you really don't want to. Okay? So you want to do this to say, this is my future career. This is a skill I want to be good at. Okay? So let's talk about this in English words. Because if I write the following out quickly in terms of an equation and then solve it out, code it out, or whatever, you understand, you can do it, who cares? We need to talk this out. Okay? So let's pretend we are an engineering discussion team and we have this problem to solve. What do you say, Michael?
Take the input of the tank at the top, and you'll get the equation of, say, area of the tank. And
All right. Okay. So, suggestion. Everybody pay attention. You guys have had me for heat and material transfer. If you are a chemical engineer, every time you start a problem, you use the golden words that never fail. Which is what? You never choose any other word other than this word while you're thinking. Let us start with a
Material balance?
huh?
Assumption.
Material balance?
If you say that, it's money in the bank, okay? You always say that. I know for you guys, it feels kind of like whatever. No, among engineers, when you say, let's start with material balance, that's kind of like, okay, hey bro, how are you doing? It's like, it's very familiar. You see what I mean? So let's start with the material balance. So the material balance goes as the accumulation is equal to what goes in minus what goes out. You see? Typically, in a material balance, it's actually more referred to as a mass balance, right? Because mass is conserved. Did you see? But in this situation here is if we have a liquid, and let's say that this liquid is incompressible, meaning to say its density is constant, right? So if we assume that we have a constant density, then mass and volume and flow rate are directly related via the density. So we can work instead in terms of a volumetric balance. Did you see? Because volume times density is mass. Okay? So you could say something like, so let's start with the material balance. And in this problem here, because we have a liquid, it's good to assume that we have a constant density. So we can instead write a volumetric balance. That's the way you would say it, right? So when I teach you and you hear me here, stop thinking in your head, I understand. Instead, in your head, go something like, let me say that again. This is a language class. This is not an engineering class. This is, I don't want to call it Spanish or Carlos, whatever. This is a language class. Do you guys understand what I mean? This is like you're learning another language. The engineering part of it just happens, that's what we want to talk about in this language. The language is more important than the engineering in your generation. I regret to say that. Okay? So, let me go back again to the language skills. So let's do a volumetric balance. So we can say the rate of change of the volume of liquid inside this tank. See? We can express that as the derivative of the volume with respect to time. It's going to be equal to the difference in flow rate going in minus going out. That's what you want to say, Michael, right? So you'll say Q in minus Q out. Did you see again? Did you see like how the words flow? Right? So we say, so we're going to do a volumetric balance. So the rate of change of volume inside the liquid is the difference between the flows going in and out. Did you notice that if you are at an engineering situation and you're able to speak it like that, like how convincing you would be in any engineering discussion, let's say a co-op, do you notice that? Right? Of course, this is the easiest stuff. As it gets harder and harder and harder, if you're always able to stick with, step by step, justify every step, and then talk it out, it's very, very hard to beat you, even if you AI'd it. Okay? Because let's pretend, again, this thing was entire AI. This is Carlos' average intelligence, Carlos' AI, okay? So this was Carlos spits that out. You had that. Then that's your PowerPoint slide. You need to explain it. Michael. Eminem. Come on, sing the song. The full thing. Do we need the points on this? Just kidding. Michael, go on, go. I know you would hate it absolutely if I'm calling on you, right? Do you know this? You would absolutely, oh, please, Carlos, don't call me. I'm not showing up for class anymore. I don't care about your 30 points. Just don't call me. No, please, because you don't get a chance to practice this. You don't ever want to be like trying to do this at a job situation for the fifth time or something. You want to be great at this, right? So use this as an opportunity, okay? Don't take me as me bullying you or, being embarrassed with other people. Hey, everyone sucks at this, okay? Go, Eminem, let's go. Let's make Michael remember. The last name is impossible, so we'll call you Eminem. Go on.
Say using a volumetric balance, we could say that the change in velocity over time is equal to the flow, the difference between the flows going in and flows going out.
You see, what happens is you're memorizing. You see, you remember? So that's why you want to memorize. Oh, you know it's not a velocity because you just said it's a mass balance, right? So remember, it's a mass balance, density is constant, so we can think of this in terms of a volumetric balance. The rate of change of volume is equal to the difference between the flow going in and out. Did you see? How about the first one? The first one's a bit harder. The first one is let's say we want to get this Q out, let's say, right? So the flow rate going out, we can think of that as the average velocity that's coming out from that orifice at the bottom. So the average velocity times the area of that hole at the bottom will be the flow rate going out. Now we need to obtain an expression for that velocity, average velocity of the fluid as it leaves, right? If the fluid has no viscosity, we can do this by energy balance from the Bernoulli's equation, for example, or even more simply as a conversion from potential energy to kinetic energy. So on a per mass basis, the potential energy of a packet of fluid at the top is what? GH, m is 1. That's equal to the kinetic energy that it will have when it reaches the bottom. 1/2 mv squared, m is 1. We canceled that already. So a little bit of algebra, the velocity is square root of 2gh. We substitute that in for q out, then we can proceed. How's that? So remember, the way I do your homeworks is pretty much pass and fail, unless you really, really butcher it or you make a mockery of me or give in completely wrong stuff, or totally don't even attempt to do a good job. I usually pass you, right? Because there's a humongous difference in, what they call if you're born from a foreign country or something, that's not your first language, of course it will be very different. I don't grade everybody on the same scale, right? But you want, as I said, you don't get a chance to practice this until it matters at co-op. You understand? There's no class like me, right? Okay? That's what's going to matter whether you get a job later or not. Okay? All right, so let's proceed. So the way we then proceed is as follows. The Q out, we can express that in terms of the height, the time-dependent variable, the dependent variable. The volume, well, if we have a constant cross-sectional area tank, let's say, the volume of fluid is equal to what? It's equal to the cross-sectional area multiplied by the height. Did you see? So if the cross-sectional area is constant, we can factor out that height from the volume. So the volume is equal to area times h. Did you see? So the area, if that's a constant, that goes out of the derivative, then you have the area rate of change in the height with respect to time is equal to the flow rate going in minus the flow rate going out obtained by energy balance, 2gh. Did you see? And so we can proceed to isolate, right, the rate of change of height, dh dt, is equal to q in divided by the cross-sectional area minus the size of the hole multiplied by square root of 2gh. Does this make sense? Right? This is, super simple, right? This is absolutely the lowest level of chemical. This is really low-level chemical engineering, right? Okay. So again, what you want to imagine is this not in front of you. You stand up here and say that out for when it's not for grade, but when it's for money. You always have to remember, when you're doing something like this, it's for money. It's for getting an offer to come back for that co-op job. I know not every one of you has a co-op job that is very demanding in terms of ability, but there are some co-op jobs out there that are extremely, extremely demanding. All right. So now, let's see what you remember from differential equations. So in differential equations, when you look at this, when you see a differential equation, what's the first thing that you need to do in your head? Okay?
Separate dh and dt.
Mm-hmm. Yeah, you could go ahead and attempt to solve it immediately, right? But every time I see a differential equation, the first thing that goes into my head immediately is it linear or nonlinear? Because the methods for solutions for linear versus nonlinear differential equations belong to two separate classes. You probably remember in ODE, your teacher in ODE made a big fuss out of linear or nonlinear differential equations. Do you remember that? Right? The chapters of the book is titled linear, nonlinear. You see the chapter titles, section titles. Do you remember what I mean? Because it's a completely separate banana on like how you go about treating to solve them and the entire way of thinking about them. Okay? So, question. Linear or nonlinear?
I have a question. So when you put like the area from the left side to the right side.
Damn it! Math skills to math. Just kidding. I'm horrible with this. By the way, is it Amira? How do I pronounce your name again?
Amina.
Huh?
Amina.
Amina?
Yeah.
Okay. Let me tell you something. Okay. At the end of this, by the way, you will notice that when I teach from here all the way to the end of the course, for process and separation, for every class I teach, I just do like this. I don't look at anything. Just no notes, nothing. Everything's like this. So as the stuff gets harder and harder, I tend to make more mistakes. Is that true, Norman? And he usually catches my mistake. Okay? And by the way, so just to explain, so the reason I do this is because it's important for you to see the process. It's not the answer. It's like how you see me struggle through everything. It makes you feel better. Hey, if Carlos is that bad with this math and he survives, you're okay. All right? So I do everything like this. But just please, on the evaluations, be kinder. Don't go off and say, Carlos, he makes so many mistakes. I have people who hate me, who just like really have to poke me on that. All right, look, I can look at my notes. I can have PowerPoint slides, but I think it's good that you see me cutting the vegetables in front of you when it's a cooking show, right? Okay. So, all right. So this thing is linear or non-linear?
Non-linear.
Huh? Non-linear. Why? The square root. Yeah. But let me ask you this. So let's say if I have another expression here on the side. So let's say if I have something like this, dx, dt is equal to x cosine t, something like that. Is this linear or non-linear? If I have something like dx dt is equal to 2x squared, something like that.
Non-linear.
How about this one?
That's not.
This is linear.
Oh.
This thing is perfectly linear, right? So what you need to focus on is entirely on the dependent variable, right? That's what you need to focus on, okay? So this thing, you would refer to that as non-constant coefficient, linear differential equation. This is non-constant coefficient. This one is immediately non-linear because that thing has an x squared. So if you have a sine x or exponential x, if your dependent variable, right? So you look at the focus on whether the dependent variable is linear or not. Okay, x squared, that becomes non-linear immediately. So the reason this thing is non-linear is because of this h to the 1/2 power. That's the reason. Okay. So now if you want to go off and solve this, is this hard? No, this is pretty easy to solve, right? Technically, you can just go off and do something like dh, right? Divided by, I could have just left the a on this side if I wanted to. So I can just go a, or your choice. So I can go something like area in the numerator, and then I go q in, right? Minus ah square root of 2gh, right? Is equal to dt. And then you go off and wiggle this, and we go off and wiggle that. Did you see? And then you got your limits of integration. Starting at time 0, right? What is the value of this expression at time is equal to 0? What is the value of height at time 0? So you have your starting height. Did you see? So you might call that, my starting height is h naught. And what happened is that at a later time t, I am interested in the height at some later time t. And you'll notice that your variable of integration, dt, and your limits of integration are the same. You never, ever, ever allow that to happen, right? So if you want to say, I'm interested in calling my height as a function of t, then at this point here, when I had these expressions here, all I cared about was that I needed to have some variable to describe time and some variable to describe h in this expression here. So usually you go off and rename these things as some dummy variable of integration. You go off and rename this. So if you want, you could have called this my actual height, time, the actual time. You need to change whatever you need to do because this time and this height are referred to as different things than this t and that h. Do you see what I mean? So if you want to call this h and t, you need to rename these. If you want to leave this as t and h, then you can't call this t and h because they mean completely different things. Does that make sense? Notice that this dt here is referring to what? Some differential time. This dh is referring to some differential height. Did you see? This is a limit of integration. You never mix those up. Okay? So in this case here, I will rename this as prime, prime, prime. And I put in the prime there, not just simply because I want to call it something else. Does that make sense? I want to change the name. I don't want to call this my height at some t, and this thing as at some time. I could do that to write down like an entire name for it. Okay? All right. So at this point here, this integration here could either be not too difficult or extremely difficult. Did you see? Why is that? The reason here is that if your flow rate going in were a constant, did you see? Then that's just a number here, 3, 4, 5, or whatever the flow rate going in. And the cross-sectional area, the size of the hole, you just shove that in. G is 9.8 meters per second squared. And this H, that's what you're integrating. Did you see? What makes this thing difficult is that if this flow rate going in is changing with time, did you see? And because flow rate going in changes with time, then naturally flow rate goes in also changes with height. You see? Then this integration is by no means easy anymore. Because this Q depends on height, and height depends on T. You see? So you can't do that. But if the Q in were a constant, this is an easy integration. Alright? Well, I'm not exactly going to call it easy, but you guys can figure that, you can find an integration table to do that. Shove that into Wolfram alpha. Okay. Now at this point here, what happens is just about in every single real world, engineering problem, almost every problem is solved numerically, right? The only time you go off and search for symbolic solutions, right, is if you intend to use that as like much further on, repeatedly over and over again, right? So that the speed is absolutely crucial and accuracy is absolutely crucial. That's when you attempt to find a symbolic integration. The vast majority of times in engineering, we don't bother. Most of the times, unless it's a very crux part of the calculation, we just do the integration numerically, almost always. Okay? All right. So what I'm going to do next is I'm going to code this out for you guys. And you might ask, why, Carlos, isn't this an AI course? Sorry, I have smoking habits. I love to code. I will never ask you guys to code, right? But let me just do this for old time's sake. I've done this for 26 years. And finally, it's reached the point where nobody codes anymore. But this is just for old time's sakes. So let me code this out for you guys in Python, if you don't mind. Just for you guys to see how this used to be done. I think all the programming languages are all going to die. That's the way it's going to do it. SpaceX XAI has it. Their intention is to go straight from intention, what do you want, all the way to machine code. You don't even have assembly or anything in the middle. That's the goal of SpaceX XI. That's the way they're going to go. And the timeline for that, they're thinking is 2 years, straight to machine code. No more programming languages in the middle. That's insane, right? But one of the largest AI companies, that's the direction they're going to go. Okay. Right. But let me just do this for old time's sake. Okay. You have no idea like how much emotion goes into this for me to code this out, knowing that this is like the last possibly vestiges of coding ever. Okay? Bear with me on this. If just a while ago I had lunch with E10. I don't know. Did he tell you?
Yeah, I ran into him.
Oh my gosh, you know everything about it. Okay, so I had lunch with him and a bunch of students from separations process dynamics from last year. And when I told them that I'm not gonna have you guys code anymore, you should have seen the reaction of their faces. Did he not tell you?
He was mad.
Huh?
He was like,
Yeah, he was like, what the fuck? That was like, I did all that pain for nothing, and these guys below me are gonna get away scot-free. Oh my gosh, you should have seen the reaction on their faces. They were furious. It's like, just make them code. That was what they said. Just let them suffer through it like we did. Why are you gonna let them off easy? Let me do this for you guys, just for old time's sake. Okay. And so what happens is over here, right? So I don't know if you guys know that, but what happens is that there is something called Visual Studio Code. Okay? Visual Studio Code. Okay?
It's not.
Yeah. So what happens is that there's this thing of a machine called Visual Studio Code, right? This Visual Studio Code right now is the most widely used coding IDE, Integrated Development Environment IDE, Visual Studio Code. It is the most widely used, right? It has versions running on Mac, Unix, everything, right? And what happens if you download for Windows, you can code this out. By the way, do not mix this up, Visual Studio Code, with something called Visual Studio. Those are two different things altogether. Visual Studio is Microsoft's programming IDE for every programming language that Microsoft uses, predominantly C#. So Visual Studio is different from Visual Studio Code, completely different things. Okay. So usually for engineers, unless you're in CS, you always just use Visual Studio Code. Even among CS people, it's usually Visual Studio Code. If you download this and install Visual Studio Code on your computer, do I have this on this disposable laptop? Yeah, I do. By the way, I need to point out to you guys, right, that this laptop I have is a 7-year-old laptop. I don't do this for any of my important work. So this is my disposable laptop. And so what I meant by disposable is because I don't have anything here that's important, credit card, passwords, I just have nothing on this computer. So what happens is later on when we use the agentic stuff, right, I basically use this computer and I have it on approve everything because I don't care. Do you understand what I mean? So for you guys, I will have you guys do all of your AI work on something called lightning.ai. I think I asked you guys to create an account there. What lightning.ai does is the following. So this is my lightning.ai. You see, this is my studio on lightning.ai, right? Have I shown you guys this previously?
Once.
I think I did once, right? I've shown you how you can get here, right? So this screen here is essentially what you would see if you installed Visual Studio Code. But isn't this freaking amazing? This is amazing because what you see here is not just exactly, but it has additional features than what you would have if you install Visual Studio Code on your desktop. But this thing all runs via the internet on a web browser, if that's not incredible enough for you. By the way, this thing only runs well on Google Chrome. Don't use any other browser. So Google Chrome. I think on Edge it might work because Edge is basically a Chromium browser, but just stick with Chrome, Google Chrome. Okay? So what I'm going to do here is you can go off and set up your project and studios all differently, right? I'm going to go here to I have a projects directory. I happen to have created that, and you'll see other stuff that I have done there. So what I can do here is I'm going to do this in Jupyter Notebook, right? So a Jupyter Notebook, that's kind of like an interactive Python programming environment. Have you guys ever heard of Jupyter Notebooks? Well, for a very, very long period of time, that was, the most educational way of coding. Okay? So let me do this. If this was last 2 years ago, I'm telling all my classes about how important it is to learn to code and how important this Jupyter Notebook is because all of the AI folks do it on Jupyter Notebook, something like this. And I have to take that all back. Such a sad day. So there's 2 ways to proceed on this. I can right-click here and install something like an IPYNB file. Or I can go over here. You see, so if you go here, it says Jupyter Notebook IDE. So I'm just going to click on that. Okay. By the way, one of the thinks that's not so bad still. If you're interviewing for a job, it's not exactly a bad idea to say that you have experience coding in Python and you're a bit disappointed that now, AI has taken all over it. No one will ever know, you had no clue. Don't lie, you never know what's gonna happen. So I'm gonna say here Python 3, right? And what's gonna happen, you see in my projects, there's now this untitled notebook, right? So let me go off and rename that. So of course my rename here. I should be able to rename that. Can you guys see this? Yeah. My hand-eye coordination is absolutely horrible. I don't play any sports, right? And even on a computer, other than the typing, I'm fast at that. Okay? I give you guys 10-to-1 odds on nitro type if you beat me. How's that? 10-to-1. $1 to $10 nitro type, okay? Okay. So what should we call this? One tank, right? Liquid level, right? So let's say like tank level, something like this, tank level. Let me zoom this in a bit. Do I know how to zoom this in? How do I make stuff bigger? Is it Control Plus? Oh yeah, it's getting bigger. There you go. Can you guys see this now? Okay. So what I'm gonna do is, let's go off and plot stuff, right? So we need to do plotting and we need to solve equations, right? So this is a differential equation. So I'm gonna go something like from SciPy, right? That, what is it? SciPy that integrate, right? Import solve IVP, something like that. Let me just shift enter that. Let's see if that works. So you might be wondering, what on earth is that? Okay, so let me show you. By the way, I need to point out to you guys, later on when we use AI and all of the code is automatically generated, guess what? You still need to look at the code. Well, to be honest with you, nowadays you don't even have to because it's so good, right? The AI generated code is so good, a lot of even the top programmers don't even bother to look at it. Who cares? We know it's going to be correct. It's at that level, right? But what happens is we'll go from SciPy integrate and import solve IVP. You will see later on when we do AI generated code, it's typing that out. It's using that. Okay? So let me just kind of show you for posterity. So what is solve IVP? Actually, solve IVP, you should probably know that. Notice that when I type in solve IVP, the first thing that comes out is this guy here, SciPy solve IVP. So let me click on that. Okay. So SciPy integrate solve IVP. Let me see. What does IVP stand for? Initial value problem. That is every single, the vast majority of the differential equations that you learn, initial value problem. You notice that, right? So solve IVP is, we're going to solve differential equations numerically, right? So this solve IVP has been one of the major workhorses for solving differential equations. Right now, it has largely been superseded by even better algorithms, but this has been around for 20 plus years or something like that, probably 30 years. It's been around since the very, very start of Python. So there's so much code written out there that relies on solve IVP. So let me show you this one. No longer because it's the best, but because it is the most widespread around, right? Actually, if you don't say anything, most of the AI will automatically go back and still use solve IVP, even though it's no longer the best, okay? Because it's just the most widespread, the most people familiar with it. So if you look at this solve IVP, and what do you have to supply? Look at this. So you have the solve IVP, you need to supply a function. You need to supply a time span. You need to say over what time range do you want to solve your differential equation. And then you need to have why not, which is the initial value. And then you have the method. How are you going to solve the differential equations numerically? There's a lot of methods to this. I'll talk about that later. And then later on, there's dense output. We'll talk about that. And then I think the other ones we can leave aside for now. Okay? Yeah. Let me go down. And so this function, let me zoom in somewhere. So this function numerically integrates a system of ordinary differential equations. So remember, this thing is a system, right? So this y here, you see this y, and that's y. That's the time-dependent variable. But this thing is for a system of differential equations. So this y there is not a single function, it's a vector function. So instead, remember we had the height of one tank, did you see? Hey, if we have 1,000 tanks in series, did you see? We were interested in calculating the height of 1,000 tanks. or concentration in 1,000 tanks as they evolve with time, then that y there will be a vector of 1,000 numbers, 1,000 concentrations, or 500 concentrations, then 500 heights of the 500 tanks. And don't look at me funny because we're actually going to do that. Right? We're actually going to have like 100, 500, 200 tanks or something like that. We'll easily do that. Because what happens is that once we have the equations sorted out, numerically, whether we extend that to 1, 2, 5, 1,000, a million, makes no difference to us. The code is exactly the same. Right? So that's the power of the coding. But what happens is, if you look at the format, you see the function that you need to supply always has to be a Python function that takes in your independent variable time, right? Followed by the dependent variable. This dependent variable there, y, again, can be vector value. Can be like, it's not just necessarily a scalar, one number. It's as many, as big as 1,000 vectors, a million, or something like that. So you might ask, well, how big do these things go? Oh, my, going to like 1 billion? It's done. So in engineering, you might ask, well, how on earth do you end up with 1 billion differential equations, right? So you need to have as many differential equations, right, as you have dependent variables. So you might ask, you can have like 1 billion equations simultaneous. Then you might ask, well, how? Well, look, if you're simulating, let's say, fluid dynamics, you're solving for fluid flow, let's say. So at every location, you have what? You have the velocity in the x, y, and z direction. Did you see? And if you have a certain domain where you have a flow that's flowing, well, guess what? At every single location, however you mesh up your thing, you have 3 velocities. Velocity in x, y, and z direction. Did you see? So you might take, how about 1 billion? Well, guess what? If, let's say, you have a certain domain, let's just pretend it's a cube, and you divide that into like 1,000 locations, 1,000 locations, and 1,000 locations. You have what? 10 to the 9th power number of what? Locations inside that cube. At every location, you have a velocity x, y, and z. And all of those velocities inside that discretized volume is time dependent. Go off and solve it. So that's one of the most challenging numerical solutions. That's the Navier-Stokes equations, the partial differential. Remember we had a bit of that, right? That's the easy. So solving these fluid mechanics problems like that ends up actually being one of the most challenging applications of these numerical methods. There's entirety of aerospace engineers in which their entire career is based on figuring out the best numerical approaches to solving these problems. There's probably thousands, or probably tens of thousands of aerospace mechanical applied mathematicians whose entire focus in their entire lives has been efficient ways of solving those numerically. You might think that up to now, you would think that that's already a closed problem. No, like up to this day, trying to improve these solvers, right, to make them even more efficient, more accurate, is not yet over. It's a continuous progression of improvement up to yesterday, or something like that. Let's keep going here. And then this y naught here is your initial values. Time is equal to 0. What are the initial values for y? Did you notice that even though we will be using AI to code this out, it is imperative that you understand this? Because do you know why? Because if you don't understand what you need to get to a solution, then you'll never understand the result you got from AI. Do you kind of understand what I mean? So let's say if you are presenting that previously, you would have, oh yeah, so this height, it's a nonlinear equation. We proceed, to solve this, right? We use, let's say, Opus 5, called Opus 5, we use Grok build, to proceed to generate the numerical solution for this. When we examine the code that it used solve IVP, right? To solve using in conjunction with the right-hand side that describes the volumetric balance. That's the English word that goes with it once you see the answer key. So let me proceed with the answer key. Let's pretend I'm your AI, but I'm coding this out in front of you token by token. Okay? Finger by finger. Okay? What's the difference whether AI does it or Carlos does it in front of you? Right? What's the difference? Okay. So now if you scroll this thing down, but you notice there's a part of this that I know you guys will miss, and I missed it. I know I will miss this so much too. Notice that when I'm teaching you coding here, the explanation is also detailed, right, like this. But later on, when we have AI doing this automated, and you got just like a pile of answers there, and I'm kind of like just explaining what each part does like that, you will miss the detail as much as I do. I know you guys love the detail as long as it's not on the example. All right, so that's the function. This is the time span. It's a tuple typically. And then if you look here, there's the method. Did you see? Remember I put RK45, RK23, doc3, right? And you have Ravelry. Ravelry is my favorite. And then you have, a PDF. What is PDF? A Bashford something here. I can't remember. And then LSODA. This LSODA has been around since like 1970s. But do you know this is still there? And you might actually be wondering, like, how come there's so many methods? Well, these are a very tiny fraction of there's probably 100 different algorithms out there of solving differential equations. And you might ask, well, why don't they just stick with one? Because there's no universally optimum differential equation solver, believe it or not. Nobody has come up with a differential equation solver that is the best for everything. Do you remember what I told you about AI? That like AI gives you an answer, but what happens is depending on exactly what you want, right? Different approaches are best. Well, these are the same thing. RK45 here is by far the simplest one. Right? RK45 is the absolute simplest one. My favorite among here is the RADAU, because I would say something like it is the most stable. And later on when we talk about stability, you might remember way back in heat and mass transfer, I said to you guys something about like, remember when we started changing the time step or the discretization step, beyond a certain point our Excel solution blows up to infinity? Still remember that, Sarah? And I was saying something like along the lines of like, oh yeah, because it's an explicit method, and for stability we need to have implicit method, and I will show you guys some more in process dynamics and control, right? So I will show you that, but maybe we'll reduce the coding of that a bit, because the coding of that is very extensive. But RADAU is a so-called implicit method. It's a very stable algorithm. And when we start doing this later on for the more harder problems, you will lose your trust in computers. Just because it's an algorithm that's well known does not mean it gives you the correct answers. Isn't that kind of scary, right? It does not mean it gives you the correct answers. Okay? All right, let's proceed with the chit chat here. Let me just keep going here. Okay? So let's proceed. Let me code this up. I'm gonna miss this. Okay. So what do we need to do? We need to supply the function that it's going to integrate, right? So we go off and we say define a function that we want to integrate. So what should we call that? Maybe let's call this RHS. You might be wondering, why is RHS? It's the right-hand side. Right-hand side. I'm not kidding you. You're laughing at me. No, a lot of people call it right-hand side. It's not just me. And so what happens is that if you look at this, right, notice that we need to isolate the dy dt, the derivatives by itself, and I put everything over to the other side that is the remainder, put it on the right-hand side, right? Depending on how far we go, you might be wondering, is it always possible to write my differential equations in this way? Are there situations where I cannot isolate dy dt by itself on this side? And the answer is yes. Those are called algebraic differential equations. Differential algebraic equations in which you cannot isolate in this way. And to solve this requires a different way of solving. Okay? And I actually made some for myself and for you guys. Of course, using AI, I'm not going to code out a differential algebraic equation solver. Usually those are very, very hard to code. And about like last month or so, I figured, hey, let me try writing my own using Cloud Opus 5. Holy moly, it was so good. I'll show you guys the result of that. And I have to honestly say, I don't understand the algorithm that was used in there, because the applied mathematics that goes into there is very, very sophisticated. Okay? So, but this is good enough. Let's go down here. By the way, I also have to admit to you guys that some of these algorithms here, especially LSODA, I don't understand what goes into there. Some of these algorithms here, RADAU, I sort of understand that. But some of the algorithms that go into here are like some of the most challenging applied mathematics that you could imagine. Okay? No, that you cannot imagine. They're that complicated. Okay. All right. So is there an example down here? Oh yeah, example down here. Yeah, so solve IVP, something like that. So let's go ahead and do this. Enough chit chat. Okay. So define right hand side, and what has to happen? We always need to supply the time, the independent variable, in this case time, right? Followed by what? Followed by our heights, right? The heights of the tank. So I think for now, let me just call this thing, I'm kind of debating here. It's okay. For the simplest one, let me just call that height for now. Then later on, we will embellish this with a different version. Okay? Right hand side dt, dh. Okay? And then after that, what do we need to do? Well, we need to return the right hand side. Remember, we have the right hand side. What is the right hand side? The right hand side is what? Return, right? What? We want to return what? We want to return q in, right? Minus the what? Minus the size of the hole, right? Right? Multiplied by what? Square root of 2gh, right? Okay. So up here, I'm going to import the workhorse of Python numerical Python, which comes to like import numpy as np. These are friends that I will really miss because these are about to disappear. Okay. Now, just to give you guys like a sense of like what an incredible thing this thing is. So something like nature, numpy, something like this. So array programming with numpy. This is just amazing. So I think I may have shown this to you guys before in heat and mass transfer. So Nature is the most prestigious scientific journal out there, right? To get something published in here is outrageously difficult. That's like almost a lifetime accomplishment for a lot of professors, right? So this is here, array programming with numpy. And you look down here, array programming with numpy has been used in everything. Physics, chemistry, psychology, but everything, right? The numpy, if you look at like GitHub pages on like all of the scientific computing literature, the amount that has been done with numpy is, oh my God, just about every engineering problem has some numpy in it. If it was done in Python, and Python probably did almost everything. Okay. So it's, but right now there's so many things better than numpy anymore. But let me stick with numpy. Okay. How many of you do you know friends from high school or something like that who said they're going to pursue data science in college? That's numpy pandas all the way. And sorry to inform them that I hope you learned other stuff. Okay. So AH multiplied by what? NP square root, numpy square root, what? 2 times G times H. I know you wanted to tell me something. No, you, Amina, is that right? Huh? Amina. Okay, Amina. So that's, am I saying it right? Amina. I know you wanted to say something to me because you keep giving me the look. You keep giving me the look that says, I think this professor is doing something wrong.
No, I don't really know.
Yeah, it's okay. And so what happened? NP squared of 2gh and then divided by what? Divided by a. Norman trusts me enough that he knows I'm not that easy. He knows that I'll figure this out eventually. So what happens is, because we need to define our variables, right? So how on earth do I insert create, no, I don't want to duplicate. How do I insert a cell above? There's got to be a shortcut key here that I'm just being stupid. Insert a cell below. How about above? Let me go up here and click that. Fine. Okay. See? So let me put in some constant here. So area. So what's the cross-sectional area of a tank? Give me a number. M&M, come on. Give me a number. 2? Yeah, fine. Okay. So units. Square meter. That's it. And then the size of our hole. What's the size of our hole? 0.1. That's it. 0.05. All right, fine. Okay. Square meters. Okay. Then what else? G. What's G?
0.82.
What?
2.
I thought it's 1. Is it 2?
Oh, maybe 1.
I don't know. I always call it 9.8. And then until some students keep insisting it's 9.81, I just find it somehow. That was such a memorable interaction. I couldn't forget it. I'm serious. I was in class one time. I can't remember the name of the student anymore. But the guy I said 9.8 because It's 9.81. He just blurted it out in the middle of the class. I said 9.8 is good enough. The student is insistent. He goes, but if we know it's 9.81, why don't we put it as 9.81? I had a good laugh on that one. All right. So you see, class participation. All right. So this thing is what? Oh, meters per second squared is acceleration, right? So did I get everything? Well, you see, at this point, we also have what? The Q in. Did you see? Right? So now we have a problem here. Or do we? Let's pretend we don't have a problem. How's this? Let's pretend we don't have a problem. I shouldn't say we don't have a problem, but we should say something like we need to think carefully about what exactly we want. By the way, this is the kind of quote-unquote problem that never goes away, even though if you have AI. This next part here. But I'm just going to put in some arbitrary number for now. Give me a number, 0.2, I don't know, right? And we'll say something like, what, cubic meters per second? That's flow rate. Did you see? Are we good? And then what else do we need? Eventually, when we want to solve this differential equation, initial value, we need to know the initial value. So h naught, the initial height is what? Give me a number. I don't know. Maybe our initial height is 1. That's it. We'll find out, right? Initial height is 1 meter. Let's say. So shift enter, shift enter. Okay? That would do. So now let's go off and solve this. So we go something like solve IVP, right? So solve IVP, parentheses, what? We have our function. So in this case, that's our right-hand side. We need to provide what? We need to provide the what? The time span? Yeah, no, not this. Yeah, I think it's the time span. Do you guys have, somebody have a good memory here? Yeah, we need to supply we need to supply the time span. So what's the time span? So we might go something starting at 0 to what? I don't know, maybe Tn, let's say. And let's define our Tn up here. Up to how long do we need to simulate this for? I don't know, what, 100 seconds? Wow. Am I doing something wrong? Who's laughing at me? Was it Sarah? Sarah was laughing at me? See, she's hiding, that's why. Sarah's laughing at me. Norman, was it an evil laugh or something? She's laughing at me or something I did wrong? Probably? Yeah, okay. It's okay, Sarah, I'll get back to you one of these days. All right, so let's say that's 100. Okay, that's in seconds, of course. Okay, same units as time. Okay, so what? Tn, oh, that's a minus. That should be an equal sign. So shift enter. There you go. Okay, so 0 to Tn followed by what? Our initial value. Our initial value is h naught. Did you see? Right? H naught. Now you notice one thing I'm going to do here is although h naught is just a scalar number, it's just by itself. Did you see? It is just by itself. Because solve IV, let me just leave that as h naught. Okay, I'll talk about that later. H naught. Let me pull that back. And then are we done? I think we are done. Well, let's find out. So shift enter. Oh no, what did I forget? I forgot something important. Oh, y naught must be one-dimensional. What's going on? What do you mean by y naught has to be one-dimensional? Well, y naught is this initial value. It's just it has to be one-dimensional. What do you mean? Well, remember, this solve IVP is intended to solve thousands of differential equations at a time. We have only one, did you see? But we still need to supply that single value as a vector of one element. That's what that is saying. Okay? Later on, if we have 3 tanks, then we need to supply 3 initial values, the height of the 3 tanks at time 0. But now we have only 1 tank, but we still need to supply that as a vector of 1 tank, right? There's a multitude of ways you can supply that, either as a tuple, as a vector, or as a numpy array. Let me just use a list, right? So I'm just going to use a bracket. You guys have all done Python a bit, right? Yeah, it's okay. That's going to be useless soon. Okay? So bracket h naught. Okay? So I take shift enter. Oh no, what's your problem? What is your problem? So NP is not defined. Sarah laughed. Okay. So up here, when I change that, you're not laughing at me. There you go. So I need to press shift enter here because I did this change, but I forgot to execute the cell. So shift enter. Did you see? Human errors that AI don't make. Okay. So shift enter, shift enter, shift enter. Oh yeah. Results. Okay. But what happened here is you'll notice that solve IVP chose times that goes from 0 to 100, and it chooses arbitrary times that are not equally spaced. Did you notice that? And it also returns back the y values, the height of the tank, as a function of time at these particular times. Did you see that? Did you notice? Right. Now, you might say that my boss wants me to plot the height of these tanks at select points, but this solve IVP went off and chose it at those points that are not even equally spaced. Of course, what goes into your head is you're like thinking, well, why the hell are they not equally spaced? How did they choose those spacing, right? So do you remember, if you guys had me heat and mass transfer, we did a lot of solving differential equations in Excel. And our step sizes were all equal, and we're using the worst possible method, Euler's method, that no one uses except by hand in Excel or in class, ODE class. So what this thing does, if you don't supply anything, it's doing it using something called RK45. You noticed earlier? Runge, Kuta. There's an F in there, Runge, Kuta, Feldberg. But the Feldberg always gets forgotten. Okay? So it's Runge, Kuta, 4-5. You're probably wondering, what on earth is those 4-5 and why is that so special? So Runge, Kuta, 4-5 is that it is solving the differential equation using a fourth order polynomial. I shouldn't say that, but you can think of it as a fourth order method, fourth order polynomial, right? And then it has this very special, genius way of doing that, in which it adds another point on those 4, makes it a fifth order polynomial. So it solves the differential equations. Remember, in Euler's method, we take 2 points. Did you see? So in Runge-Kutta 4-5, it's a fourth order polynomial. Instead of a straight line, fourth order polynomial using the points you have solved earlier, right? And then it does it again using a fifth order polynomial. But the genius of Runge-Kutta-Feldberg is that the fifth point can rely on the previous 4 points that were solved already. So the RK45 does not require 9 function evaluations. It requires only 5. 4, and then a fifth one. There's a level of genius there that's amazing. That's why it's so famous. It's one of the earliest amazing algorithms. Okay. But anyway, so you might ask, well, why do we need to do it using fourth and then fifth? Because what you do there is you solve it using a fourth order method, then you solve it using a fifth order method, and you compare the accuracy, you compare the results. If the difference between those two is too big for your accepted relative tolerance, then what does it do? It shrinks the step size. So what it does is it starts out with a particular initial step size, and if the errors are much less than your tolerance, based on its estimate from the fourth and fifth order solution, it increases the step size so that it gets to your final result on the other side efficiently in time. When you're solving millions of differential equations, speed is a very big deal, okay? And so you notice when we were solving stuff in Excel, we're taking like 1,000 steps or 10,000 steps arbitrarily. We have no regard of what the error or whatever is, right? This thing adjusts the step size to keep the local error within our relative tolerances. So you might ask, well, what is the tolerance that we put in? Well, we did not put in a tolerance. We just relied on the default tolerances. So here, where are the default tolerances? So you see, there's the R-tol and A-tol, which are the default tolerances. And the default values is 1 in 1,000 and 1 in 1,000,000 were absolute tolerances. If we want more accuracy, then we just change those and make them smaller. We will do that later, okay? Is everybody with me? Okay. All right, so let's keep doing this. And so what happens? You might say, well, I want my solution at the points of my choosing. Did you see? And so for that purpose, what happens next is, and we go off and we go something, comma, dense output, right, is equal to true. You see? Dense output is equal to true. And also at this point, I would always put in my favorite method. My favorite method is called the Radeau method. It's the slowest of all the methods there, but it is the most reliable in the sense that, like, when the other methods fail, they diverge or they become unstable. Radeau is usually the most stable. Remember, computers make mistakes, round-off errors and these things, right? So this method here, Radeau, of the one that's the standard, is the one that is most reliable. It is an implicit method. That's good enough, I think, for now. Later on, we'll go into more detail of what exactly that means. So when I press Shift Enter here, no, they need to be the same, I think. I think my codes need to be the same. Yeah? Okay. So you notice everything looks identical, except there's a change. There's now this attribute, which is referred to as your solution object. You see? So this is the results. Of this result, there's a solution object. There's a solution attribute, sol. Did you see? So let me yak that solution attribute in. So if I assign this thing to, let's say, res or result, but I'm lazy, so let me just call that res, something like this. Shift Enter. Then now, if I type in something like res.sol at, let's say, give me a number, 2.3, Shift Enter, what is that? Well, that is my height at a time of 2.3 seconds. So res.sol, you can think of it, it is actually a function, it's an interpolating function. So res.sol, you can give it any time that you want, it gives you back the height. Does that make sense? Right? And so at this point, I want to plot my results. So I might go into here and say something like this. I might go something like Shift Enter. T, the times for plotting purposes, right? I might go something like numpy linspace, equally spaced points, linearly spaced points, from time 0 to tn. And how many points do I want for plotting? Let's say, I don't know, 100 points. So if I press Shift Enter on this, let me put a lowercase here, right? T, something like that. So if I look at T plot, I basically have 100 numbers there, from 0 to 100. I should have probably used 101 instead of 100, because you know, fence and sticks, right? There's 101 sticks and 100 gaps in the middle. Right? So let me leave that as 101, let's say. Okay? So those are the times at which it will be calculating it. So notice if I go now res.sol and I evaluate that using tplot, using that vector of times, it evaluates the whole thing. So it evaluates the values, the 100 heights, 101 heights associated with those 101 times. Does that make sense, everybody? You guys with me? Just curious, have you guys done something like this way back in first year? If, you know, you guys have done this, right? You guys have used Sol IVP? Something, okay, that's fine. Now, one thing you'll notice here is that this res.sol.tplot, you notice that at the front here, what is the dimension of this array? Did you see? So if I look at the end of this, if I put in that shape, if I look at the shape of that, look at the shape of that. That's a 1 by 101. It's a matrix. It is a matrix of 1 row and 101 columns. Did you see? So you might ask, well, why on earth would you add this as 1 row and 101 columns? Did you see? So if you look at this, it is annoying. Did you see? The first time you see this is annoying. So you see this, there's 2 brackets there. So it's denoting as this thing here, the one on the inner bracket, this here, right? That is your first row. Your 1 row with 101 columns. That's annoying until you realize again that solve IVP is intended to solve a lot of simultaneous equations. So later on, if we have 3 tanks, which we're about to get to, then what's going to happen is you're going to have 3 rows, and each row is 101 columns. So for now, we just have 1, okay? So what I'm going to do here is I'm going to go bracket 0, because I'm just going to get that first row. Remember, Python indexing starts at 0. You see? So you go Shift Enter on this. Now you see it's exactly the same, except that now I don't have that bracket in front. Okay? So now I can refer to this as what? This is my maybe H for plotting purposes. You see? H for plotting purposes. Okay? So now I want to create a beautiful plot. And so I can go, one of my favorite, there are two major plotting libraries out there, right? The 2 major plotting libraries are matplotlib, right? Matplotlib, that's a big one. And the other one is Plotly. Usually, if I am using for Python for direct like publication onto a website or something like HTML file, something like that, I would use Matplotlib. But if I'm using it for an interactive session with notebooks, I use Plotly. And the reason is Plotly allows me to change the size of my figures, zoom in and out, and do manipulations interactively in that Jupyter notebook. Matplotlib will not let me do that. But the most widely used plotting library out there is Matplotlib by a long margin, right? So a lot of like the magazine illustrations that you have, like these things, are done in Matplotlib, or there's something else called 3JS, that's in JavaScript. But a lot of the scientific publications are done in Matplotlib. Okay. Plotly is also used a lot too. Let me kind of show you a bit of a Plotly. Plotly is a JavaScript library that has a Python interface. So Plotly is used a lot in Java. When I say JavaScript, does that ring a bell to you guys? So basically anybody doing web programming for browsers uses JavaScript, right? And Plotly that's the original version of Plotly. It's for JavaScript, it's for websites, plotting beautiful plots of JavaScript websites. What happens is that there's a Python API for this, so you can still also do this using Python. Did you see? So if you look at examples, absolutely stunning plots, right? Where are my examples? There you go. So you can make just about any possible plot that you can imagine, right? So multi-panel plots, ternary diagrams, pretty much everything. Okay. So I go something like, from Plotly, that's subplots. I know, import make subplots. You're probably wondering, Carlos, why are we talking subplots here? Because I'm an engineer. So by an engineer, there's no such thing as in which I make a figure with a single plot. Almost always when I make plots, I have like 2 plots side by side or 4 plots in a panel. To me, there's no such thing as a figure with 1 plot. I always use multiple panels. So this is just the way I've memorized this. Right? I always subplots, whether it's a single one or multiple one, I always just use subplots. That's my memory, right? So bear with me. Okay? There are many, many ways to achieve exactly the same results of plots. All of this will be automated eventually. This is just for old time's sake. This might be the last time I code in front of you. Okay, so let's do this. So I can go something like, let's create a plot. So we go something like fig is equal to make subplots, right? Make a subplot, right? Make subplot. And then we could go something like fig.add scatter, right? The x values are my times, and my y values is the height h plot, something like this. What? Make subplots. There you go. How come it's not showing up? I hate this. So what happens is that in Visual Studio, there's something I need to put in there. You see, am I out of time? Still 9 minutes, right? Yeah, give me 9 minutes here. So figure not appearing in VS Code plot. There is I need to do something here. So I need to say something like I need to put in something like this. You see up here. So plot renderers default, right? Okay. So I need to copy this, right? So import plotly.io as PO, right? So up here. So something like import plotly.io input output as PO, right? And then up here, I need to set where the renderer is going to appear, where the results are going to appear. So I can copy and paste this. Control C, and then Control V, something like that. The PO, the renderer's default, is to put it into the connected notebook, something like that. I think that might do the trick, I hope. Okay. Did it? This is annoying. So fig.show. Oh, there you go, finally. It's probably the fig.show. That's not appearing. And then again, for old time's sakes, because Sarah here is going to be talking to Ethan, right? Of course, I always have to say something like template is equal to plotly dark, because it hurts my eyes, something like this. I've been saying that line for probably over a decade, repeatedly over and over again, because it sounds cool. So now it gives me, what's your problem? I thought it's it's not template, it's not this. Okay, I'm sorry, not here. Control X. I need to go something like figure dot layout. I'm sorry, I forgot this. So I think it's plotly adjust layout or set layout, something like this. Let me see. Update layout. You see, I've forgotten this stuff. So I go something like update layout. Use update layout. And I think it says something like the width, maybe, I don't know, set the width to, let's say, 600. And then height to, let's say, 400. And then template is equal to plotly dark. Okay? You know, there was a time in which I would spend so much time like making just the most perfect plots, right? You know, with, of course, you know, you need to label this, you need to label that, you need to label everything, make it look nice, especially with a lot of panels, dots, and these things, the labeling. And I would spend so much time Googling, trying to find out what is exactly the correct way of doing it. No one memorizes that, all the different options, right, of making a plot. AI does that all for you nowadays. Life is good, okay? Life is good. So I have 6 minutes left, okay? That was kind of fun. Except that now, here comes the conceptual part. That's very, very important. Because this part here, whether you have even if you have AI, it's absolutely crucial. So when you see this, what goes into your head? So in English words, let's say you saw this, and that's what we did up here. How would you describe this to your boss? Like this. So we did all of that, you see this result. What do you say in English words? AI did it for you. Average intelligence did it for you. With all the mistakes. You see, I did it for you. Now you explain that. What's the story you would make up? I'm not asking you to lie. What's the story you're going to say? So let's explain. So do you remember earlier, I said something like H naught, and I said Q in. Did you see these two values here? And I said something like, this is something. And I said something like, this is concepts that we need to be wary about. Initial steady state. Do you remember all those words that I said? It's all tied to this. Because if you look at this, what happened here? Do you notice what happened here? So let me ask you, so was the system at an original steady state? No, because the initial height, I forgot what number I gave it, right? This original height that I gave it up here, this original height of H naught is 1, right? It's not the steady state height that you would obtain for this flow rate of 0.2. It's not. Did you see? So we started the solution of this initial value problem not at a steady state condition. Did you see? But what happens is that as we run it for a long time, to let's say 200 seconds, so if we run it for a long time, eventually it reaches a new steady state. Did you see that? Right? That's very important because remember, this entire class is about deviation variables, right? In relation to some initial steady state or some nominal operating conditions, which is almost always some steady state, initial steady state. So over here, we need to say something like this. If we want to start this simulation at an initial steady state, we need to have the correct height initially. So how do we do that? Well, let me do algebra. Let me do algebra on the screen so I don't have to switch to paper. So how do we do this? Well, if you're at steady state, this right-hand side needs to be 0. Did you see? Because the derivative is 0. That's what a steady state means. Did you see? So if I set this equal to 0, look at this. So Q in is going to be equal to AH, right? Times this, square root thing. Let me just write this down. Times square root of 2GH, right? And then I have the area. So the area, and then divided by area. Well, the area, I just need that to be equal to 0. Did you see? I need this to be equal to 0. Did you see? So I move this to the other side. That needs to be 0. So what do? I divide both sides by AH, divided by AH. I divide both sides by AH. Did you see? I square both sides, there's a square root, so I square both sides. I'm just doing algebra on my keyboard, okay? Because I don't want to switch to paper. This is simple enough. So I go off and square that. Did you see? I square that to get rid of this square root. Did you see? Right? And I still have that 2g. So I divide both sides by 2g. So I divide this entire thing. So I go something like h naught is going to be equal to, h naught is going to be equal to, just bear with me for a second. Give me a, please. And then close parentheses divided by what? 2 times g. Does this make sense? Right? So I basically solve for that initial steady state. Guys, give me 2 minutes. There's no rush like doing with that bad thing because it's just really, annoying me. Okay, please. It's personal. Just kidding. I'm just kidding. Okay, so shift enter. How's that? So now you notice that if I go off and run this, damn, nothing happens. And you're gonna complain to me, I like the previous one better because it was more interesting. Did you see? Now, again, concept. So what we do at this point, remember everything is in terms of deviation variables. It's not just the dependent variables, but all the parameters in the system are with respect to deviation variables. So if we say something like, there's a change in input of the flow rate, again, it's deviation variables. The flow rate going in changed by 1 or changed by 0.2. What that means is that this Q in at this variable, it changed by how much? Did you see? So what I'm going to do here, I'm going to define this thing over here as Q in naught. That's your initial nominal operating condition for that flow rate going in. Did you see? But this actual Q in over here is now the Q in that depends on time. And I can say that starting from time is equal to 0, that let's say this Q in, let me say something like this. So let me put in something like, let's say Q in is equal to 0.3, let's say. So what that means is that at time is equal to 0 and all subsequent times, my flow rate going in there increased by 0.1. The deviation of the flow going in is 0.1. That's the deviation variable for Q in. Did you see? So shift enter, shift enter, shift enter, shift enter, shift enter, shift enter. Okay? Of course, I could have chosen a lower one too, then it would have gone down, and you would have complained to me and said that looks the same. But no, because we are building the foundation here for an entire course. I'm emphasizing the word deviation variable. Now stay with me, don't leave, okay? Don't leave. You're forbidden from leaving. So notice over here, just chill for a second. No one's gonna, just wait for a second. So Q in is gonna, let me abuse your time, okay? So I can go something like np.sine, right? What? Well, my flow rate going in can be sinusoidal, right? So I can go something like 0.1 times t, let's say. And what's my magnitude of my oscillations of the flow going in? 0.1, let's say. And I add in my steady state. So I have 0.1, but what happens is that my flow rate going in is oscillating. Did you see? Yeah, what do I do? So you expect the height of your tank to oscillate. Did you see? But now let's say what happens is we are a spaz. The flow rate going in changing very rapidly. Did you see? So this flow rate going in, instead of having a frequency of 0.1 radians per second, it was, let's say, 10. What happens? Well, you expect the height to oscillate very fast too. Did you see? But notice what? Did you notice the amplitude of this oscillation is shrinking? Look at the height of this from 0.82 to 0.81. Did you see? Let me increase the number of points here. Okay, let's say 1,000, something like that. Okay. Okay. And so, that's a bit too much. Okay. So you know this next, actually. I think I'm going to stop here. I don't want to abuse you guys too much, right? But this will be a continuation from here. Okay. Let me save this out.